Hello, everybody. How are we doing tonight?
Hi, Professor. Doing good.
Good. All right. Let's see. Oh, okay. Apparently Zoom did an upgrade or an update or something. And I said, okay. And now I got to figure out what I did to myself. But I think we're okay. Everybody can see the screen with the square spread footings.
Yes, I can see that.
Awesome. Thank you. Okay. So we actually have a little ways to go. We got to finish. This was lecture 15, and I hope to at least start lecture 16 tonight. And we are getting close to the end. So does anybody have any questions they would like to ask of me as we start before we get into resuming our lecture?
Is lecture 16 going to be on the finals? Because it's on retaining walls, right?
It is on retaining walls, yes. No, the scope of the final will not include the lecture on retaining walls. It may include this lecture on square spread footings because we did some homework on footings as well. I know it's kind of pushing towards the end there, but the footings may be on the final. Retaining walls definitely will not be on the final.
All right.
Good question. Anybody else? Okay, so let's make our way through the rest of lecture 15. We talked last time about strip footings or a wall footing, where in and out of the page, the footing could be infinite in length when we only deal with a 1 foot width at a time, kind of like a one-way slab where we just deal with a 1 foot wide section of what could be 20 feet wide or 200 feet wide. We're just dealing with it on a per foot basis. Square spread footings, however, you don't do that. On square spread footings, we look at the whole footing and we have to look at it in both directions. So that's the key difference between spread footings and wall footings. Let's put there. Okay, so square spread footings are designed much like strip footings, except now we design for the total shear and total moment, not a shear or moment per foot like we did on a strip. Spread footings also have some additional shear checks that need to be made. Namely, we're going to be looking at punching shear. That's the big thing that we're going to add. The footings can now fail in shear along 2 sides, each of which must be checked. And 2 sides means that it could fail on the north or south side, but it could also fail on the east or west side. So like 90 degrees apart from each other. And a new shear failure mode known as punching shear must also be checked. The first shear, known as one-way shear or beam shear, must be evaluated on 2 sides. Okay, so here's a square footing. Here's our column that's being supported in the middle. Here's a side view of the same footing. There's your main flexural reinforcement at the bottom of that footing with 3 inches of cover to the bottom, 3 inches of cover to the side. Notice that one layer of steel is going east-west, the other layer of steel is going north-south. And on a square footing, it's completely arbitrary which is going which way. In fact, you have no idea which way the contractor is going to be laying that steel. So you have to make your worst assumption. If D is less for the steel on top than it is for the steel on bottom, then we're going to be conservative and just assume that we're designing the steel on top. Like the strip footing, we find shear at D from the face of column. So in plan view, that distance right there is D, where D is the distance from the top of the footing to the center of our steel. So D from the face is basically at a 45-degree failure crack in this direction here. VU1 for shear is equal to QU times the shaded area. So VU along this plane at D from the face of the column is equal to QU. Remember, QU is the factored soil pressure times the area of everything beyond where that shear plane is. Because there's QU down here, all this QU has to be transferred through shear to get into the column. Or if you look at it, the load is coming from the column. All that load, the fair share of it that goes out here has to go through this concrete and shear to get to this bearing pressure out here. We also have shear in the other direction, 90 degrees to the first check. So now we just looked at shear along this surface. We could also have shear along this surface. So this surface is going to be equal to, again, QU, but now it's times this hatched area being resisted by this plane. And you might think, well, why do I have to bother doing it on two sides? Aren't they the same? Well, they're not always the same. A square footing, they may be the same, but only if the column is square as well. If the column is a rectangle, then even a square footing has slightly different areas on either side of the column, because the column has different sizes of faces on it. And a lot of times these are not square, they're rectangular. So B and D will be different. So that's why, generally speaking, I mean, unless everything is absolutely square and identical, generally speaking, you got to do your check on one side and the other side to see which side will control your design. VU2 for beam shear is equal to QU times the shaded area again. Notice though, D1 is not equal to D2, even if the footing is square, because of the way that the steel is sitting on top of the other steel. The main flexural steel in one story must sit on top of the steel in the other direction. D1 can be assumed to be H minus 3.5 inches, but D2 is assumed to be H minus 4.5 inches. So remember, the cover has to be 3. So it's just a kind of a get you in the ballpark to assume that the center of the steel is a 1/2 inch up. So that's 3.5. But to get to this top row going in the other direction, you add another inch, and that makes it 4.5. Now, if you're talking number 10s, number 11s, number 14s, you might have to refine that. This is just to kind of get you into the ballpark. And that could be refined later. But these are some good general numbers to get you into the ballpark. Everybody tracking? Any questions so far? Okay. Now we have a new failure mode that is unique to square or rectangular footings, and that is two-way or punching shear. And what happens with punching shear is the column will take a truncated cone of concrete and just blow right out the bottom of the footing. So it fails in shear along all 4 sides. That's why it's called punching shear. When the failure surface is D/2 from the column face on all 4 sides. So one-way shear, you check it at D from the face. Two-way shear or punching shear, you check it at D/2 from the face. That's a key difference. VU3, or your design shear VU, is equal to your factor QU times the entire shaded area. Because when this thing fails, the unshaded area punches through with the column and the shaded area stays right where it is. So your VU is QU times the entire shaded area. We have some new parameters here. ACI 318, section 22.641 states that the critical section has a perimeter B naught as shown below. So B naught is this perimeter. It's all four sides. It's measured in inches. So it's the length of this perimeter. And the perimeter is defined as D/2 from the face of support on all four sides. ACI 318 section 22.652 defines the shear strength VC as the lesser of. We have A for lambda square root F prime C B naught D, or B 2 plus 4 over beta, and this is not beta 1, this is just beta. So 2 over beta lambda square root F prime C B naught D, or C 2 plus alpha sub S D over beta naught lambda square root F prime C B naught D. So the square root lambda square root B naught D is common to all three. So really what you want to do is just calculate 4 or 2 plus 4 over beta or 2 plus alpha S D over B naught, and whichever of these three is the least, then you multiply that times lambda square root F prime C B naught D, and that becomes your VC value. Where beta is the ratio of the long to the short side of the column. So clearly if the column is square, beta is equal to 1. If the column is say 24 by 12, then beta is equal to 2. It's the ratio of the long over the short. Alpha S has three possibilities. It could be 40 for an interior column, like I'm showing here. It could be 30 if this column was located right on the edge of the footing, then that would be an edge column, and that's 30. Or it could be 20 if the column is located right in the corner of the foundation, then alpha S is 20. Bending moments. Okay, so any questions about shear? That was shear in the east-west direction, shear in the north-south direction, and punching shear.
For alpha 2,
Yeah.
does it have to be just in the edge? It doesn't matter if it's edge in the middle, edge in like the lower middle or something, as long as it's in the edge.
Good question. I wonder if ACI has put some definition on that, like how close to the edge before it's considered the edge, how close to the corner before it's in the corner.
Mhm.
And I'm thinking, I have to go back and check that, but I'm thinking the definition is, see this beta naught? If beta naught is completely in the concrete, then it's 40. But if the edge encroaches on this beta naught, then it's an edge column. And if the two edges encroach on beta naught on two sides, then it's a corner column. I think that's how I would interpret it.
Okay.
All right, so bending moments, unlike shear, shear is defined on a plane that's D from the face or D/2 from the face for punching shear. The moments you calculate right to the face. Moments are calculated right at the face of the column. The critical section is at the face of column. And due to symmetry, the bending moment will be the same in each direction if it's a square column, right? So if it's a square column, then this bending moment along this dotted plane is going to be the same as that bending moment. But if they're rectangular, then you have to evaluate each one independently because you have a different area in a different moment arm for each direction. Even if the bending moment is exactly the same because everything is symmetrical, you still have one row of steel lower than the other row of steel. So one direction is going to be less effective than the other direction for resisting that bending moment. So the general practice is to design for bending with the lesser D. See how I've got this here? See how D1 is right to the center of the lower, and D2 is to the center of the upper row of steel. Common practice is that you don't design one side for D1 and the other side for D2. You just design the whole footing to be conservative with D2. Whichever is the lesser D, that's the one you're going to use. And then you just use the same steel in both directions, and the other direction will be a little bit conservative. Okay, so example number 5. Here we got a footing. This is a spread footing supporting a column load. The column is not square, you notice. It's 18 on one side, 24 on the other side. The dead load being supported by the column, the dead load is 875 kips. The live load is 220 kips. F prime C of all the concrete is 4,000 PSI. Fy, the yield of the rebar is 60 KSI. And gamma C is equal to 150 pounds cubic foot for the concrete. There is no soil overburden in this condition. Other dimensions are given in the illustration. And this one is going to be square. So I'm saying B is equal to D in this example. So it's a square footing. QA from the soils report is given as 3,500 PSF. So what is required? Design the size of the footing to safely support the given loading. Design the footing for shear and flexure. Solution. First step is to guesstimate the depth of the footing. So we just blindly go in there and say, what about 14 inches? What do you think? 14 inches, is that good for over 1,000 kips of load? Probably not, but that was a place to start. So Q is equal to P over BD, P over A, plus the weight of the footing. I don't have the weight of the soil because there's no soil in this example. So I have 875 plus 220 is a 1095. That's the kips load coming down through the column. I solve for required B. So Q is equal to P over A plus weight of footing, less than or equal to 3,500 PSF. So I set up my equation. 3,500 PSF is equal to 1095 over B squared. This is actually BD, but D is equal to B, so I can just make it B squared, plus my 150 times a depth or thickness of concrete of 14 inches divided by 12. And that gives me a square root function, and I solve for it and I get 18.15 feet. So let's make our footing 18'6" wide. Okay, now one thing to really hit home on this, because I see a lot of problems, a lot of students get confused about this. When I am designing the footing size to satisfy a soil allowable, I use service loads. I did not factor this by 1.2. I did not factor the live load by 1.6. QA is an allowable stress level. So I need to find a Q that is less than QA based on service loads. When we get to the part of this example, when we start designing concrete, then we're going to shift over to factored loads. Okay, so keep an eye out for that. The loads are service when I'm dealing with soil pressure. The loads are factored when I move to concrete design. Okay, so calculate the shear demand VU. Now that I have a guesstimate of the depth of the footing and I have a preliminary size of footing, now I can work on my shear demand. Why do I do shear demand first? Why don't I do my flexural design first, like we did with beams?
Because you might need to change the measurements.
Yes. In beam design, if the flexural steel doesn't work, you typically have to make the beam deeper. But if the shear doesn't work, you just add more shear steel. For footings, it's the complete opposite. If the shear doesn't work, we don't use shear ties, so your only recourse is if the shear doesn't work, you got to make the footing deeper. Usually, whatever depth you need to make the shear work, the flexural demand will work just fine with whatever depth you used to make the shear work. It's the complete opposite of beam design. So you design for shear first because that's what's going to set the thickness of your footing. Okay, so for shear design, now I've got to factor my loads because I need to find VU. The little u stands for ultimate, so I need ultimate loads. So my factors are either 1.4 times the dead load is 1225, or 1.2 times dead load plus 1.6 times live load. That's 1402. 1402 in this case is going to control. That becomes my design load. I already determined that my footing is 18.5 by 18.5. I'm not going to resize it because I have a factored load. But what I'm going to do is figure out what the factored bearing pressure will be based on the factored load and the actual size of the footing. So QU is going to be 4.096 KSF. Even though Q was less than 3,500 PSF, that doesn't matter. I can't use Q to design my footing. I need QU. So QU is 4.096 KSF. Now I've brought my soil pressure to the factored level. My axial load is at the factored level. I can now determine what my factored shear demand is. D is going to be H minus 4.5. Again, for a square footing, I'm just going to design to the less effective row of steel. So I take the height minus 4.5. That gives me 9.5 inch effective depth. So VU is equal to QU, the pressure, times the width of the footing, times, let's see if I can kind of draw this in here. Times that depth. So you have a width in and out of the page, and you have a length. So that's what's in these parentheses is the length. The length is half the footing, 18.5 over 2, minus half the column, which is 18 divided by 2 divided by 12 to get to feet, minus D. So half the footing minus half the column minus D gets you, this is what's left. So minus 9.5 over 12 is D, and that all gets me 584.2 kips. So all of this pressure out here times the width of the footing is 584.2 kips. Everybody following this? Any questions on this? Okay. That's my demand. What's my capacity? My capacity is VVC. So for a footing, VVC is phi times 2 times lambda square root f prime c BD. We talked about last time, lambda for footings is almost never anything other than 1. So we plug it in here, phi is 0.75, 2, the 1 is in here somewhere, square root 4,000 times B is 18.5 times 12, and D is 9.5. And that gives me a grand, massive total of 200 kips. 200 kips is not even close to 584 kips. So we start all over. Let's try something much more reasonable. Let's say 30 inches. But 30 inches is heavier. So I have to recalculate my footing pad size in order to still be under 3,500 PSF. So I recalculate it, and I now find that I need to be 18.72 feet on a side. So we're going to just go a little conservative and say 19 feet wide. So everybody following this? I started with a guess of 14 inches, and I needed a pad that was 18.5 feet wide. I go to 30 inches. I've added 16 inches of concrete to this, and now I need to be 19 feet wide to keep my allowable soil pressure under 3,500. Now that I know it's 19 feet wide, I can recalculate my factored soil pressure to be 3.884 KSF. D is 30 minus 4.5, so that's 25.5. VU is the new soil pressure, 3.884, the new width, 19, the new depth, 19 over 2 minus 18 over 2 minus 25.5 inches. And that gives me my new demand is 488.9. It's kind of interesting, right? Is the load itself didn't change, but by making the footing thicker and making the footing wider by a little bit, look at my shear demand. It went from 580 to 480 just by making those changes. My capacity is again 0.752 square root of prime C. B is now 19 feet wide. D is now 25.5 inches. And we get a capacity of 551.6, which is greater than 488.9. So we are now acceptable. We have something that works. I have a question. Can you explain the VU again? Can you clarify which part of VU? VU is the factored shear on this plane. $18.5. Oh, here. Okay. All right. Let me do this. Okay. Let me try to do it a little different. This is a plan view of this footing. So I'm just taking this footing and looking straight down on it. And there's the column in the middle of that footing. And by ACI, the shear plane is right there. That if it's going to fail in shear, it's going to fail along this plane. Okay. And then I can say, this distance from here to here is D. Okay, so from the face of column to my shear plane is D. D is the same D as you see right here. So what is the VU? What is the force along this plane? The force along that plane is equal to the soil pressure, QU, times this area, right? A force is a pressure times an area. So the pressure is QU, or right here, QU, and the area is the area that I just highlighted in blue. But how do I get this area? I don't know this distance, but what I do know I know the distance halfway. I know that distance, and I know half of the column is that distance, and I know this distance is D. So I can take half the footing. I know that distance, that's 19/2. I take away half of the column, that's 18/2, and I take away D, which is 25.5. What I'm left with is that dimension, which is what is the whole, what's inside the parentheses left over is that dimension. And I know the width is 19 feet, that's that dimension. So pressure times width times length equals a force. Did that help? Okay. Okay, great. Good question. Okay, so I now have a footing thickness and a footing size. 19 by 19 satisfies my bearing pressure, and 30 inches deep satisfies my shear demand. So far, so good. So far we're saying 19 by 19 by 30 inch footing. But now we need to check the punching shear, which is totally different than the one-way shear that we just checked. Now we're going to check punching shear, where it fails along all four of these perimeter lines here. So my three limiting cases, case A, case B, or case C, where, and again, beta is the ratio of the long to the short side of the column. In this case is 24/18, it's 1.33. Alpha sub S is equal to 40 because this is an interior column. Beta naught, okay, and this looks a little cumbersome, but all I'm doing here is the length of this side is the width of the column, 18, plus D/2 plus D/2. So D/2 is 12.75 inches. D is 25.5 inches. D/2 is 12.75. And I have one side and another side. So I got 18 plus 2 times D/2. And then on this side, I've got 24 plus 2 times D/2. So 24 plus 2 times D/2. And then I've got 2 long sides and 2 short sides. So that's times 2 times 2. So if I start here and I start measuring tick, 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 and I measure all the way around, I get 186 inches.
And that's the perimeter, right?
That is the dotted line perimeter that we assume if this thing's going to punch through the footing, that's going to punch through along those lines. Yes.
Okay.
Okay. So case A is 4 square root F prime C B naught D. Lambda again is taken as 1. 4 square root B naught D equals 1199.9 kips. Case number 2 is the same thing, but 2 plus 4 over beta. So 2 plus 4 over 1.33 is 1499.9 kips. Case 3, 2 plus alpha D over beta. Alpha is 40, D is 25.5 over, not beta, B naught is 186. And that gives you 2245. Of the 3, A is the one that controls. So VVC is 0.75 times 1199.9, gives us a load of, or a capacity of 899.9 kips. What's the demand? The demand is the soil, factored soil pressure times everything that is hatched. So the easiest way to do that is here's my soil pressure, 3.884, times the whole footing, 19 times 19, minus the length of this wall times the length of that, or side, the length of this side times the length of that side. So there's my 18 plus 2 d over 2 times 24 plus 2 times d over 2. So basically the area of the whole footing minus the area of this hole. And that gives me a demand. Oh man, I got a demand of 1,344.1 kips. What does that mean?
It's not enough.
It's not enough. So what can I do? What do I have control over?
The thickness.
That's right. That's exactly right. I do not have enough thickness on my footing. I was hoping solving it for one-way shear would give me a thick enough footing. But in this case, punching shear controls, so I have to go thicker. I was trying to make a 30-inch footing work, and it didn't. So let's try a 36-inch footing. And we start all over. So D is equal to H minus 4.5 again. Now we're at 31.5 for D. Beta naught is again 2 times the width of the column, D over 2, length of the column, D over 2. Beta naught is 210. A. And here you can see I'm just plugging in my new numbers for beta or B naught, and that's 1673. I already know that case A is going to control, so I'm not recalculating B or C, just recalculating the one I know that controls. So V times 1673.5 is 1255.1. And my new, actually, this isn't completely correct because I didn't redo. Going to a thicker footing changes my bearing pressure.
Yeah,
would-
I was gonna ask, like, if you change the thickness, isn't it B will also change?
Actually, no. B might change. I have a 19-foot wide footing. B might change if 19 doesn't work. I wonder if I check that. But this number doesn't change because remember, QU does not include the weight of the concrete footing. So by making the concrete footing thicker, I did not change QU. As long as the size of the overall footing stayed the same, then QU is the same. Okay, so let's run with it for a moment. So again, the shear demand is QU times the whole footing minus the hole in the middle. And now we're at 1345.4, and it still doesn't work. 1345.4 is greater than 1255.1. 36 is still not good enough. Let's try 40. Spreadsheet would really come in handy about now. But at 40, I am going to check my footing size. So I solve for B, and I've outgrown the 19 foot. Okay, so darn it, I got to go to 19'3". So I recalculate QU. Again, I didn't have to recalculate it as long as the footing stayed the same width, but now the footing has to be a little bit wider, so that changes QU. So now QU is 3.783 instead of 3.884. D is 40 minus 4.5, which is 35.5. Beta naught, again, column 2 times D, column 2 times D over 2. And B naught is 226. So recalculating equation A, I plug into 226 and the 35.5. I get 2,029.7 kips. V times 2029 gives me 1522.3 kips. I think I finally got it. 3.783 times the whole footing minus the hole is 1318.2 kips. Aha, we now have a footing that works. Gonna recheck my one-way shear because I added quite a bit of weight to this thing. And my one-way shear is, the demand is 430.9. My capacity is phi times 2 square root f prime c. My width changed to 19.25 and my depth is 35.5. So I've got 778 now, way better than 430. So we're good. So shear, one-way shear and punching shear have been satisfied with a few iterations with a 19-foot 3 square footing at 40 inches deep. Any questions on the shear design? As you can see, if you're doing this, even in a homework problem, if you wanted to, but certainly if you're doing this to make money, I would build this into a spreadsheet. And then that way, all these can be programmed into cells. You can just iterate through different depths and width of footing rather quickly and really kind of hone in on the most efficient answer. But for illustrating this in a lecture, I chose to leave it in this format so you can see where all the numbers come and go. Okay, flexural design. Again, the assumption is however deep and big the footing needs to be to satisfy shear, it's going to work for flexure. Since the footing is square, the flexural demand will be equal on both sides. So the side with the lesser D will control. We're going to use an effective D of 35.5 inches. Actually, the flexural demand is not exactly equal because the column is not square. The column's rectangular. So to go to this face, you have more hatched area than to go to this face, right? Because this face is 12 inches off center. This face is only 9 inches off center. So you got 9 more inches of area about this face. So this becomes my design case because this is going to produce the greater moment. Okay, so to calculate mu, I take QU, which was the final iteration was 3.783, times the width, which is 19.25, times the depth or the length of this. The length of this is going to be 19.25 over 2 minus half the width of the column, which is 18 over 2. But the moment is the resultant, which is at the center of this hatch part. So the resultant is QU times B times L, but then the moment arm is from the center of the hatch to the face of the column, which is going to be this length over 2 again. So that's why this is squared over 2. And that calcs to be 2868 kip feet. That's a pretty big moment, but you got a lot of concrete here to resist it. All right, so now this becomes a singly reinforced rectangular beam problem. It's a really shallow, wide beam, but that's okay. It's still a singly reinforced rectangular beam. So I use my reinforcement index, R sub n. I plug in my moment times 12 to get the kip inch. Phi is 0.9. The width is 19'3" or 231 inches. And the depth is the effective depth of the footing to the rebar, which is 35.5 squared. This equals 0.131 KSI or 131 PSI. Using table A13, I think we had 4,000 PSI concrete, 60 grade rebar. So using table A13, I find that rho, and I interpolated it up, but rho is equal to 0.023. So the area of steel required is rho times B times D. So 0.0023 times 231 times 35.5 is 18.86 inches squared. That's a healthy amount of steel. The minimum temperature and shrinkage requirement is AS minimum is 0018, but remember, temperature and shrinkage is not rho times B times D. It is the minimum value 0018 times B times H. Temperature and shrinkage is based on the gross section. So that's why you see 40, not 35.5. And that requirement is 16.63, which is less than 18.86. So 18.86 controls my design. If I go with number 10 bars, then I can use 15 number 10s. The area of a number 10 is 1.27 inches squared, which I looked up in the table. And so 15 times 1.27 inches squared is 19.05 inches squared, greater than 18.86. So I'm done, right? Call it a wrap, say it's done.
So that 15 number 10, it's just in like one side, like let's say horizontally or something, like the first layer.
It is, okay, so this is my hatched area.
Mhm.
So this is the plane that it's bending about. So my reinforcement has to go left to right.
Right.
Okay, so my 15 number 10s are 1, 2, 3, all the way to 15. That's what they look like. They have to be basically the whole width of the footing minus 3 inches on either side, because the moment could be on this side or the moment could be on this side. And we're gonna, what I was leading you guys up to is we're not done yet. But one of the things we're gonna do is check the development length, because you have to, right here at this critical section, you have to be fully developed on both sides of this critical section. This side is the shorter length. So you have to be fully developed on this side of this critical section. And we'll check that in a minute. But you could also bend about this line or this line. So you also have to have reinforcement here. 1, 2, 3, all the way up to 15. They have to be in both directions. That makes sense?
Does that mean you technically need 30 number 10s?
Yes, it does. You need
Okay.
15 number 10s in each direction. Yes. And we've already built into our equations that one set is going to be sitting a little higher up than the other set, because one set has to sit on top of the other. We don't know which is which, but that's okay because we designed for D to be to the top layer. So we're already taken care of. Okay, but back to my question for the class. If AS required is 18.86 and AS provided is 19.05, am I done? Did I do my due diligence?
Not yet.
Why?
You still need to check the PMN.
That is right. That is absolutely right. That's what I was looking for. I am still correcting homeworks where students are neglecting that very important step. The homework number 7 that I just graded, of course, was dealing with columns. So the check was phi PN greater than PU. But you always have to check that. That is always the final step. Is phi mn greater than mu? Is phi vn greater than vu? Is phi pn greater than pu? So on and so forth. Just because we went through these steps and we chose 15 number 10s, I don't know if that works. I don't know if there's a mistake in this equation. I don't know if there was a mistake in this table, or did I make a mistake here? There's all kinds of places where I can make a mistake and I won't catch that mistake. I won't know if I'm creating a dangerous situation unless I check my phi mn greater than mu. This is the only thing that matters. Everything else was just steps to help you get to this point. This is the only thing that really matters in that check. All right. So when I do the check, I put in my chosen steel, I put in the grade, I put in D, chosen steel, the grade, 1.7 F prime C, width of the footing, and I get 35,770 kip what? Kip inches. That's another point. I still see a lot of mistakes being made that this answer is kip feet. But all the units in this are inches and kips. So this has to be kip inches. Divide by 12, you get kip feet. So phi mn is 2981 kip feet greater than 2868. Now I know I've got a good design. Now I can say use 15 number 10s at 16 inches on center each way. OC stands for on center, EW stands for each way. How did I get 16 inches? That was a question that came up in office hours. How did I get 16 inches? Well, the first bar has to be 3 inches from the edge. The last bar also has to be 3 inches away from the edge. So what I did, 19.25, 19'3" is the same thing as 19.25 feet. Times 12 is 231 inches. 231 inches is the overall width minus 3, so minus 6 inches is 225. The center of the last bar to the center of the first bar is 225 inches. If I have 15 bars, that means I have 14 spaces. 225 divided by 14 is 16.07 inches. So there's 16 inches on center. Okay, we did that. We did that. We checked. Okay, the last thing, now that we have the footing size, we have the footing depth, we have the reinforcement in the footing, last thing we need to do is make sure that we have enough development on those bars at my critical section. Critical section is at the face of column where you have your maximum moment. And so I need to be sure that what is available in the length of this bar meets or exceeds the code minimum to develop that bar. That's what I need to check. Remember this equation from a few lectures ago? So I can put in my parameters. This is normal weight concrete, so lambda is 1 for normal weight. Psi sub t is 1. These are not top bars, they're bottom bars, so psi sub t is 1. Psi sub e is 1. These are not epoxy coated or galvanized bars. Psi sub s is equal to 1 because these are number 10 bars. CB is the smaller of half the spacing, so 16/2 is 8, or the center of the bar to the nearest face is 3.5 inches. That's going to control. KTR is equal to 0. There are no ties. There's no transverse steel in this thing. DB is 1.27 for a number 10 bar. And so I plug in my numbers, 60 KSI, F prime C, psi, 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 and 3.5 over 0.75. I can't take this term greater than 2.5. So I substitute 2.5 and I get 36.1 inches. That's my requirement. How much do I actually have? I have half the width of the footing minus half the width of the column here minus my edge distance 3. And that gives me 100.5 inches. So 100.5 is much larger than 36.1. No issues there with the development length on my footing. So here's my final design sketch. My footing's 40 inches deep. It's 19'3" wide, 3 inches of cover, and I got 15 number 10s each direction. Okay, any questions?
I have a question.
Sure.
So, can you go back to when we were looking for the shear demand and then the shear punch? Since we're like designing it, can we solve for the shear punch first? And then does it automatically, if the phi yeah. So if we solve for the shear punch first, does it automatically, the shear demand is gonna be like way above our
well,
VU?
there's a few problems. First of all, it's not readily available to solve it directly. The first problem is you don't know if punching shear will control over one-way shear or vice versa. And I, quite frankly, when I created in these examples, these examples were created from real jobs, by the way. The column size was from a real job. The load on the column was from a real job. So I wanted to give you something that was more real world. A lot of times the textbook gives you examples, but you're not going to see that in the real world. That's not representative of a real column design. So I took real columns from real jobs with real loads and then made up a footing and went through the design process. And I was actually surprised how deep the footing had to be. And I was also surprised that punching shear controlled. The jobs that I've done, real jobs, one-way shear controlled over the punching shear. So it just depends on the column size, the allowable soil pressure, all kinds of variables. So number one, you could come up with something slick that solves for D directly in one-way shear and then find out that punching shear controls like I did here. Or you could come up with something maybe that solves D directly for punching shear just to find out that it didn't control. So that's the first problem. Second problem is D is in your PVC equation here, but D is also embedded in B naught here and here. So D is in this equation as well. And then there's 3 of these equations. And again, you don't know if A or B or C is going to control. So there's too many layers to the onion, I think. Really the best, I mean, I've been doing this for a while, and if I had to do this, I would use Excel, plug it all in, have it spit out instantly, spit out the capacities of failure mode A, B, and C, and one-way shear, have as inputs H and B. And you just put in H equal to 30, B equal to 18 feet. Soil pressure doesn't work. Okay. H equal to 30, B equal to 19 feet. Okay, soil pressure works. Oh, two-way punching shear doesn't work. Okay, let's try 40. Oh, that works fine. How about 38? Oh, 38 works. Okay, 36? Nah. Okay, we'll go to 38. You see what I'm saying? You would iterate on the solution very, very quickly. It would just take you, I don't know, an hour or two to plug in an Excel sheet to make this into a spreadsheet.
Okay, so it depends on the design as well. And then for the spacing, uh, okay, I was thinking of it like when you were building the footing, does the column is like with the footing,
No,
or is it like it's sitting on top of it, or is the footing
yes.
is hollow or something?
No, no, no. The footing's not hollow, but let me get to here. Come on. There we are. Okay. In the field, they will use a backhoe and they will dig this hole out of the ground. So the ground has been, you see them driving around with those big scrapers, the big caterpillar scrapers. They grade the earth. So when they grade the earth, they bring it to at the elevation that they need. They bring it to a levelness that they need. And they also bring it to a compaction level that they need. All of that is done by the contractor responsible for the grading and what's the word I'm looking for? But anyway, the preparation of the soil. Once the soil has been prepared, then you bring in the guys, another contractor with a backhoe. He digs out this square shape wherever these columns exist. Once this shape has been dug out of the ground, this is a hole in the ground. They will put chairs or adobes to keep the rebar off the soil, and they will tie a mat of steel and drop them in the hole. Literally just drop them in the hole. And then they'll check to make sure they have 3 inches on the side, 3 inches on the bottom. Everything looks good. They bring in the concrete truck and blub, 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 blub. They fill up the hole with concrete. Usually what they'll do is have some dowels sticking out of the top here. I didn't draw them in this diagram, but they'll have steel kind of shaped like this, sticking up out of the top of the footing. So when they pour the concrete, they pour it to the top of the footing, nice and level. They'll come back and finish it with trowels and whatnot. And that's the finished concrete. Once that cures for a little while, then they'll come back and start building the columns by dropping in a cage with long steel and ties and everything that we talked about during the column designs. And they'll put in wood forms or steel forms to form up the column, and they'll pour the columns in, but the columns go in like a month later after the foundations. And then you just keep going from there.
Okay.
Okay. All right. Next topic, we're going to take a break here. And this is a long presentation I'm beginning to realize. So I'm thinking tonight might just be lecture 15, and we might do lecture 16 on Thursday. That's the way it's starting to smell. But let's take a 10-minute break. Let's come back, I don't know, say 6:15. Let's come back at 6:15 and we'll finish out lecture 15. So we'll be back in a minute. Okay, I'm back. Let's see. Okay.
Sure, but I need to share the screen. Do you want me to do that, or do you want to wait till the class ends?
Well,
Yeah.
I'm kind of rushed. I don't know if we're going to be able to finish in the time that we have left. Can you ask it without sharing?
Okay, so I don't know. So for homework 7, the question number 2, that after you commented here that you said for the column design you found 408, which I calculated again, but it looks like everything looks correct. And I don't know. Also, you decreased like 1 point for that question, but overall grade you gave me like 18. I don't know.
Okay, well, yeah, that's more specific.
Right.
That's more specific, which we can address. Can we do it on office hour? We have another office hour Thursday. Can we talk about that?
Yeah, yes, sure.
Okay. I'm pretty sure about that 408 because quite a few students got the same number I did. So why don't we investigate and see what went wrong? But we could do an office hour offline.
All right, sure.
Okay.
I think that's the one that I asked you, Professor, about the book did differently.
Right.
And
200,
then
page 271, right?
yeah, that one. And then what you did is you just shortcut the AST is equals to rho G times AG.
Right. Yeah, so I found 361 inch square, and so, but anyway, we can speak about it later, so we have a lecture now.
Okay. Yeah, let's do that in office hour because we got a long ways to go and running out of time. If that's okay. Okay, the next topic that we have is instead of square footings, rectangular footings. So rectangular footings are designed much like a square footing, except the flexural reinforcement in the long direction will control, and so should be placed on the bottom layer. ACI 318 section 13333 states that a percentage, and they call it gamma S, of the flexural steel on the short side must be placed in a band equal in length to the short side dimension, where gamma S is equal to 2 over beta plus 1, where beta is the ratio of the long side to the short side of the footing. So what they're basically saying is you have a rectangular footing. So the green outline is something where you have a much longer side and you have a short side. The flexural steel running along the long side has a much longer moment arm than the steel on the short side. So the long side's going to control. Let me draw this in here. So this steel is going to be a much more severe demand than the short steel. So you design this long steel first and you put it on the bottom row, you put the short steel on the top row. But what this is saying here is that a percentage of the total steel needs to go in this hatched area. And then the rest of the steel goes out here. And the reason why you don't make it equal, the reason why you kind of bunch it up within this hatched area is the mechanics of the actual footing. It's going to, most of the stress is going to be in this short area, not so much on the long area. So we assume the bearing pressure QU is uniform over the whole thing, but it really isn't. The soil is really more like a bed of springs, and where the load is, that's where you're going to have the most deformation. So the code addresses it by requiring this requirement. The balance of the short side reinforcement is evenly distributed in the end regions. Oh, well, that is surprising. That was the end of that one. That was slide 308. I am so confused.
Yes, I am so confused why you say like we have long lecture, but we don't.
Yeah,
Because I thought you are going to go for the retaining wall.
well, we are, but that was really confusing. I thought we were on slide 308. We were actually on slide 500 and something. So, hey, we did it. We got through lecture 15.
Wait, you thought that you're gonna have a example for rectangular footing?
I thought I had like another 200 slides.
Oh,
Well, sorry guys, that's it for that one. Okay, so that's actually good news. That gives us a little breathing room.
wait,
So what?
I have a
Yes.
question for that rectangular footing.
Okay.
So when you say that percentage of the short rebar is gonna be on that hatch area, does that mean your spacing will be different for the short ones?
Yes, it does. Yes, it does. So what that I gave you that equation, kind of blew through it kind of quickly, but the gamma S equation, if gamma S comes out to be say 0.75, then what that means is that 75% of all the steel you going in the short direction needs to be located in that hatched area. And only 25% of that steel goes into the ends, like 12 and a half and 12 and a half on each side. So absolutely, you're going to have a different spacing. Just for example, you could have like a demand of number 6s at 6 inches on center in the hatched area, and then only number 6s at 12 inches on center outside the hatched area. So it is forcing you to have an uneven spacing, which is exactly what they want to kind of counteract the effect that the soil will be putting more pressure on the middle region and a lot less pressure on the outside region.
Right, and then the short rebars is always on the top.
Yes, short
Okay.
rebars on the top, long rebars on the bottom.
Okay, that makes sense.
Okay. Again, sorry about that, guys. I got discombobulated. It was a 520 something slide presentation. What I was looking on my left screen that you can't see said I was still in the 300s. So I was like, oh man, how am I going to get to this in 40 minutes? But it wasn't keeping up with what I was doing on screen. Okay, so we actually did all 500 and something slides for that presentation, which means we can actually start tonight's lecture. And we have roughly 40 minutes or so, maybe a little less, to see how far we can get on lecture 16, which is good news because what I wanted to do is at least do a good start. And lecture 16 is not nearly as long as lecture 15. So I wanted to get a good start on lecture 16, finish it up on Thursday, and then have plenty of time left over to take questions and talk about the final or anything else that you want to do in this course. So that's the plan. Hopefully that makes sense. And so before I do jump into lecture 16, which is our last lecture for the semester, does anybody have any questions they'd like to ask about square footings? Okay, let's jump into lecture 16. Tonight's lecture is on retaining walls. What is a retaining wall? Retaining walls are concrete walls designed to resist horizontal or lateral soil loads. So there's your classic section through a retaining wall. You have a grade up here, you have a lower grade down here for whatever reason. You have a footing where we have what's known as the toe, and we have the heel of the footer. And then we have a wall that is built integrally with that footing. And that wall retains or holds back the soil pressure from this dirt up here. You see these things everywhere. I don't know if you recognize it or immediately say, oh yeah, I've seen those everywhere. We build these things everywhere. I guess really a common example would just be along the sides of freeways. Wherever a highway or a freeway cuts through a hill, they put retaining walls on either side to retain that soil. Some of them get quite large. I'm pretty sure if you go over the Kellogg Hill, you got some pretty good sized walls on either side of the Kellogg Hill, retaining all that dirt so that the freeway can be at a lower, straighter elevation. You see them in new home construction. You see them everywhere. They could be as little as just a couple feet right here to form a planter box in your backyard. This could be 60, 80, 100 feet tall, just depending on the application. Some of the retaining walls that get pretty large, you can't tell by just looking at them, but I mean, you can see some pretty big ones. On the 10 freeway, the 91 freeway has some really tall retaining walls. When these get to a certain height, it is no longer practical to just cantilever the wall off of the footing. And so what you don't see is that they have anchors. And so a different kind of retaining wall is where they may have soil anchors that go back and anchor into bedrock. And they could have many layers of these things that go back and anchor into solid rock. And so the soil is pushing against this, but these anchors are holding it, tying it back like cable stays into solid rock. I know that's what they did on the 61 or the 91, because I remember watching them build it as we drove by every day, and they had several layers of these rock anchors before they covered it up with concrete. Tonight's lecture, though, or the lecture for this class, is going to be much, much simpler. We're not going to deal with post-tensioned or anchored walls. We're just going to talk about cantilevered walls. In addition to the structural design of the concrete wall and footing, retaining walls are governed by Chapter 18 of the current building code, or the International Building Code or California Building Code, for the failure conditions of overturning, sliding, and allowable soil pressure. The typical procedure is to consider, again, a 12-inch wide strip of wall and resolve all the forces on that section to check overturning, sliding, soil pressure, and then to design the concrete portions to the prescriptions of ACI 318. So overturning, sliding, and soil pressure are all service level checks. And then the concrete portion that you design is factor loads to ACI 318 for concrete design. Several soil parameters must be determined and are typically investigated and reported on the project soils report. As a minimum, the soil's unit weight, gamma, the lateral active earth pressure, C sub A or gamma, or equivalent fluid pressure, gamma effective, coefficient of friction, mu, and allowable soil pressure, QA, must be known to design the retaining wall. All of these Greek letters and factors and things would come from a typical soils report. Like the spread footing design, surface level loads are used for the soil portion of the problem, overturning, sliding, soil pressure, as I just mentioned. And factor loads are used for concrete strength designs. Okay, active soil pressure. Active soil pressure is the lateral pressure from gravity pulling down the weight of the soil. The magnitude of the lateral pressure is a fraction, C sub A, of the density of the soil, gamma, and is dependent on soil parameters. Okay, so if you had just dirt, just a big lump of dirt, and you went in there and you cut yourself out a cut like this, what's that dirt trying to do? An unsupported cut of soil will tend to slump, as shown. So you got the weight of all of this is being pulled down by gravity, which produces lateral pressure. That lateral pressure will tend to push the soil out. And again, it is totally dependent on what kind of soil we're talking about. Sand will behave in one way, clay a totally different way, and rock, just good old bedrock, you could cut a cut of passageway, if you will, a cliff, if you will, in solid rock, and it's not going to go anywhere. So the magnitude of this behavior is totally dependent on the type of soil. If the soil is contained by a wall, right? So we make the cut and we put a concrete wall in here, it will develop an active soil pressure that is similar to the behavior of retaining fluid, like water behind a dam. So it's going to create a pressure that starts at 0 at the top and reaches a maximum at the maximum depth that's being retained by the wall. Because the pressure from active soil pressure and from retained water are so similar, many times the active soil pressure is defined as an equivalent fluid pressure, gamma EF. When given in this form, then the lateral pressure at any height from the top of the wall can be found by multiplying the equivalent pressure by the height. So if you guys remember from physics or fluid dynamics or somewhere, that the density of a fluid times the depth of the fluid gives you the lateral pressure that that fluid is exerting on other fluid next to it or to a dam or a wall that is next to it. So if the fluid, like water is what, 64 point something pounds per cubic foot. If you have 1 foot of water, at the bottom of that foot, you got 64.5 pounds per square foot. 10 feet down, you have 640 pounds per square foot, so on and so forth. So the force P at any depth X is equal to the height of X times the density of the fluid, or in the case of soil, times the effective fluid or equivalent fluid pressure, right? So the soil may weigh 120 pounds a cubic foot, but it may have, just because of its properties, its soil properties, really, based on its soil properties, it may have an equivalent fluid pressure of 30 pounds a cubic foot. So it exerts pressure on the wall the same as a fluid with 30 pounds per cubic foot density. Or it may be the same as a fluid with 50 pounds per cubic foot density, right? So that comes from, again, the soils report. And they're going to give you, based on the tested parameters of the soil, they will report to you, the engineer, what the equivalent fluid pressure is. Where P sub X is the pressure at some arbitrary point down from the top of the wall. The active pressure at the base of the wall, P sub A, is equal to the equivalent soil pressure, gamma EF, times the total wall height, H. The total lateral force on the wall then is denoted as H sub A. So P sub A is the pressure at the base of the wall. H of A is the resultant of all the pressure on the wall. And it is equal to the sum of the active soil pressure along the whole height of the wall. Okay, so here's my pressure diagram. P sub A is the pressure at the base of the wall. The wall is H high. H sub A is the resultant of all this pressure, and H sub A is a force, right? So P sub A might be 1,000 pounds per square foot. H sub A might be 4,000 pounds. H sub A is equal to, again, it's the resultant of this stress block. So because this is a triangle, it's equal to half times PA times H, which is equal to half times gamma EF, the equivalent soil, equivalent fluid pressure, times H squared. H sub A is located at the centroid of the triangle. So it's located at 1/3 of the wall height up from the top of footing, or 2/3 of the wall height down from the top of the wall. Okay, any questions so far? Okay, we have this thing called passive soil pressure. And passive soil pressure is completely different than active soil pressure. Passive soil pressure is the resistance of soil to movement. Okay, so active soil pressure is gravity pulling the dirt down, and it's trying to bulge out. Passive soil pressure is the dirt is already there and you're trying to press into it. So active is creating a load, passive is more like a reaction. It's resisting something moving into it. For a retaining wall design, the passive pressure would help to resist the active soil pressure trying to move the wall. So the weight of gravity is pulling the soil down, pushing the wall to the left, but the wall doesn't want to move to the left because you got dirt over here that doesn't want to compress. So this dirt on the left-hand side of the footing would tend to help resist the active soil pressure. However, passive soil pressure is also defined by the project soil report, but for retaining walls, it is generally and conservatively ignored. Why? Why would you ignore the soil over here that's helping you? Any ideas?
Too small.
It's very small. That's one reason. There's two other reasons I can think of. Reason number two is that once you build this wall, how do you know that the soil in front of this wall is not going to erode away, blow away, be dug into, or disturbed in any way? You can't guarantee that. This wall could be there for 50 years. You don't know what's going to happen to that dirt. So that's reason number two. Reason number three is that passive soil pressure really only works on undisturbed soil. So you can't dig this out and then kind of pack it back in there. It doesn't really work that way. So you'd have to come in here and excavate really carefully to leave this soil undisturbed. And then you have to pour the concrete right up against it. And it's just not really worth it for that small. So for those reasons, generally speaking, even though it's there and it could help you, we're going to ignore it. Sliding resistance. So the total active soil pressure lateral force, H sub A, is generally resisted by sliding friction, labeled R sub S. So here's my setup. The soil is trying to push the whole wall and footing to the left. As I just said, we ignore the passive pressure here, but what we don't ignore is you get a whole bunch of friction on the underside of this footing. So the footing wants to slide, and the soil friction underneath it is what keeps it from sliding. That's our main mechanism for the whole thing, not just moving to the left. This resistance R sub S is equal to the weight of the wall, the weight of the footing, and all the soil. Or let me, I didn't really draw that in, so let me draw that in. And the weight of all the soil that is bearing on top of the footing times the coefficient of friction. So in other words, if the wall and the footing were to move, say like a foot to the left, all this dirt would move with it a foot to the left. So the weight of this dirt actually helps in clamping down the whole assembly and creating friction. And then the coefficient of friction, mu, varies with different kinds of soil, and that comes from the soils report. The building code, section 1806.1, this is not ACI, this is the California Building Code, specifies that the factor of safety for sliding must be 1.5 when using service loads for the check. ASCE 7, that's another code book that gives us loads. Section 2.4.1 specifies that D, L, and H loads all have a factor of 1 when calculating the sliding and the sliding resistance. But the code, the important thing is that the code says that you have to have 1.5 times more capacity than you do demand. And that's just a factor of safety against these things sliding. If, oh boy, I did that sneaky, what didn't I? Okay, from this slide to this slide, look what I did here. If the sliding resistance from friction is inadequate to resist the applied lateral load, then a choice that you could do is you could build a keyway into the foundation. The key can be built into the underside of the footing. And when you do so, oops, I didn't explain it, but when you do so, if you build this key, now you get some real passive pressure down here, because this soil down here at the bottom of the footing is not going to erode away. And it's not that difficult to dig out a little keyway and leave this undisturbed. And it does help quite a bit. So this is a common solution. And then you calculate the passive pressure against that face there, and you add it to all your sliding friction. And that may be enough to get you to that 1.5 safety factor.
So you have like 2 passive soil?
Yeah, you have this that you ignore over here, but you have this down here that you actually count on. Yes.
Okay.
Okay, overturning. We have to look at overturning too. The active soil pressure would tend to overturn the footing about the toe. So that's the toe. You have this force with this lever arm that's tending to rotate the whole assembly over. And that does happen. These things will fail. It will take this whole concrete assembly and just flip it over. And so that we have to make sure that doesn't happen. So we need to add up the overturning moment. OM is the overturning moment, and that is equal to the lateral force H sub A time is eccentricity all the way down to the bottom of the footing, because it's going to rotate about the toe here. So we calculate OM, and then we calculate our resisting moment RM. And RM is equal to the weight of the stem wall, the soil above the footing, and the footing itself times each times the eccentricity to the toe. So like the weight of the wall times the distance to the toe, the weight of the footing to the distance of the toe, and the one that I showed was the weight of the soil times the distance to the toe. All of these forces tend to hold that foundation down whilst the soil force tends to overturn. The building code, again, section 1806.1 specifies that the factor of safety for overturning must be 1.5, again, when using service loads for that check. So same idea as sliding. You add up all the loads that tend to flip the footing, and then you compare them to all the loads that tend to hold down the footing. And as long as the capacity is 1.5 times greater than the demand, then you have an acceptable design. Okay, you could have live load. And we actually did a job down in San Diego that looked just like this, where, let's see, what did they have? They had a roadway down here, and they had a railway up here. So the trains are running up here and the cars are running down here, and they had a big retaining wall. So the trains put down a pretty significant live load, and that live load is applied up here at the top. So the procedure is, if there is live load applied above the wall and the retained soil, then it can be added to the lateral load as an additional lateral pressure equal to an equivalent additional soil equal to the live load divided by the equivalent fluid pressure. Okay. In other words, say that, let's just use some round numbers. Say that the equivalent fluid pressure is 50 pounds a cubic foot. And this live load up here is 100 pounds per square foot. Well, if the live load is 100 pounds and the equivalent fluid pressure is 50 pounds, then all you do is you remove the live load and you put another 2 feet of dirt up here. And then you add up your soil pressure with that additional 2 feet of dirt. So whatever the live load is, you divide it by your equivalent fluid pressure, and you add that much more dirt on top of the whole thing and figure out what your soil profile looks like. Does that make sense?
Yeah.
Okay, and that only really works because the load factors are the same. If the load factor for the live load was different, then it wouldn't be as easy. But because the allowable stress load factors on everything is 1, then you can just do 1-to-1. Okay, for concrete design, the stem wall is designed for bending and shear. The critical section for bending is just at the top of the footing wall interface, and the critical section for shear is located at D, the effective depth of the wall section, up from the top of the footing. The footing is designed just as we did for strip footings. The soil pressure must be evaluated with non-uniform pressure due to the overturning moment. Retaining walls are usually designed with the wall portion battered back. That way, when the wall rotates and deflects under the lateral loading, the top doesn't look like it's leaning over. So here's the illustration. Usually, walls are thicker at the bottom where you need more thickness and are thinner at the top where you don't. And they batter them back like this, like maybe 6 inches. So if this wall leans over under this loading by 2 inches, it doesn't look like the wall's about to fall over. But if you made this wall straight up and down and it's leaning over 2 inches or 6 inches, it like, oh, what's wrong with that wall? Looks like it's going to fail. So that's why they batter it back like that. The wall flexural reinforcement is placed on the back side with the proper coverage. It's on the back side because all the load is trying to push the wall out, and that puts the tension on the back side, compression on the near side. Okay. Any questions, or are we ready for an example? Any questions, or do we want an example? Go ahead. I'm sorry, I interrupted. Go for it.
I said the example.
Okay.
So real for the example.
Okay. Okay, let's see. I think. Okay. Yeah, all right. Okay, so here's the example. I have a traditional retaining wall. The foundation is 30 inches deep by 14 inches wide by, it could be hundreds of feet long. That doesn't matter. We're going to design it on a per foot basis because the in and out of the page, again, could be 10 feet, could be 100 feet, could be 1,000 feet. The dimensions of the footing locating the wall are 3.5 feet and 9 feet on the back span. This is pretty common that you'll see that the footing is narrower on the front side, much longer on the back side, so that it's like a shovel. It picks up all this extra dirt for stability. The wall itself is 17.5 feet tall, and it goes from 18 inches wide at the base to 12 inches wide at the top. The soil parameters, gamma of the soil is 110 pounds per cubic foot. The effective or equivalent fluid pressure is 40 pounds a cubic foot. I'm sorry, one second. Let's see. No, way back here. Huh, weird. Okay. Okay, so the coefficient of friction against sliding, mu is equal to 0.55. All three of these would come from the soil report. QA, the allowable soil pressure, is 3,500 pounds per square foot. That too comes from the soils report. For the concrete side of it, we're going to use normal weight concrete. We're going to use 4,000 PSI strength on the concrete, 60 grade rebar. Okay, so the first step is calculate the loads. What's my demands on this structure? So we calculate the active lateral pressure, which is equal to the pressure, P sub A, is equal to the equivalent fluid pressure times the height. So that's 40 pounds a cubic foot, plus 17.5, plus the thickness of the footing itself is 2.5 feet. Gives me, or times a width of 1 foot, gives me 800 pounds per lineal foot. That's my pressure. And see, that's at the bottom of the footing here. Because the pressure, you think it's just on the wall, but the pressure's on the back of the footing too. And that adds to the whole thing trying to be sliding over. So don't forget about the back of the footing. H sub A, the resultant of all that, is 800 pounds times the total height times half, which is 8 kips. And the eccentricity, this is a big triangle, so it's a third of the triangle is your resultant. So 17.5 plus 2.5 over 3 is 6.67 feet, or 6'8". The overturning moment then is going to be 8 kips times 6.67 feet is 53.4 kip feet. The resisting moment, okay, so we need to add up the weight of each one of these elements. P1 is the footing. P2 is the triangular slice of the wall. P3 is the rectangular slice of the wall. P4 is all the soil over the footing. P1 is 150 pounds a cubic foot times a height of 2.5 feet, a length of 14 feet, and in and out of the page is 1 foot. That's 5.25 kips. P2 is 150 pounds a cubic foot times the height of the wall times half, because it's a triangle, times a width of 6 inches times a in and out of the page of 1 foot. That's only 0.66 kips. P3 is the rest of the wall. That's 2.63 kips. And P4 is all this soil. The soil is 110 pounds a cubic foot times a height of 17.5 times a length. Remember, this dimension here is 9 feet, and that's 17.33 kips. So the total, if I add all these together, is 25.9 kips. That's the total weight. Now we need the moment arm for each one of those components. E1 is equal to the 14-foot length of the footing over 2, 7 feet. E2, remember this dimension was 3.5 feet, plus this is a triangle, so 2/3 of the 6 inches gives me 3.83 feet. E3 is 3.5 feet, plus the 6 inches, plus half of the 1 foot wide. That's 4.5 feet. And E4, 3.5 plus 6 inches plus 1 foot plus half of the 9 feet, and that's 9.5 feet. Okay, so I have a mass and a moment arm for each one of these 4. So my resisting moment is, you add them all together, 5.25 times 7 is 36.8. 0.66 times 3.83 is 2.5. 11.8. And the soil, that's the big one, 17.3 times 9.5 is 164.6. So you can see clearly how much a contribution of all this backspan of soil is to stabilizing the whole structure. Total 215.7. So my factor of safety is 215.7 over my demand was 53.4, and that's 4.04. 4.04 is clearly better than 1.5, so we're okay for overturning. Next, we're going to calculate sliding resistance. As we found in the first part, the total mass of the structure is 25.9 kips. My sliding resistance, R sub S, is mu times P. Mu is 0.55, P is 25.9. I get 14.2 kips. Factor of safety then is 14.2 over 8 is 1.78, which is greater than 1.5, so that's okay. If this had been less than 1.5, you either have to make the foundation bigger to grab more mass of soil behind it, or you go to a shear key to add that whatever's missing, you would pick that up with a shear key. And finally, let's check our soil pressure. For the purposes of soil pressure, the eccentricity is measured from the center of the footing. Okay, so each one of these 4 elements is measured from the center of the footing, because what we're doing is a P over A plus or minus MY over I check. The arm for the foundation is 0. It's right in the center of the foundation. E2 is 7 minus 3.83, which we got from the first part, 3.17. E3 is 7 minus 4.5, 2.5. E4 is 7 minus 9.5, minus 2.5. So the eccentricity to the center is 0, 3.17, 2.5, and this is on the other side, so it's negative 2.5. Find the moments. Overturning moment of 1 is 0, 2 is 2.1, 3 is 6.6, and 4 is 17.3 times minus 2.5 is minus 43. Total sum is 18.8 kip feet. Now, what I want to mention is don't forget your H sub A, your lateral pressure. So your lateral pressure is adding to these 2, and the soil is opposite. So there's your lateral pressure, 53 plus 2 plus 6 minus the backspan soil. You get a total of 18.8 kip feet, and which is overturning counterclockwise. So pressure is P over A plus or minus MY over I. P is 25.9. A is 14 by a 1 foot width. is 14 feet squared. Y is 14 over 2, 7. I is BH cubed over 12, which is 1 times 14 to the third over 12, 228.7 feet to the fourth. Therefore, Q, I just plug in all the relevant values, and I get 2.425 kips per square foot, which is less than my allowable soil pressure of 3.5, so we're okay. Okay. This is a good place to stop, I think. This was the 3 service level checks. We just did overturning moment, sliding, and bearing pressure. And then when we pick it up on Thursday, we'll start doing the concrete design with the factored loads. Okay, so any questions for me for tonight? Okay, hearing none, let's draw this to a close. And I will see you all for our last night on Thursday. Everybody have a nice night.
Thank you, Professor.
Thank you.
Professor.
Thank you. See you Thursday.
Thank you.